Hello friends, in previous lecture we have studied totally boundedness, epsilon net, etc. And we proved the result a metric space is compact if and only if it is totally bounded and complete. Now we will take the result. We have proved the result a metric space X is totally bounded if and only if every sequence in X contains Cauchy subsequence. That result we have proved. Now we will take theorem a metric space is compact if and only if it is totally bounded and complete. Okay. So a metric space is sequentially compact if and only if it is complete and totally bounded and totally bounded. So first we will prove necessary condition. So let XD be sequentially compact metric space. Compact metric space. So by previous result, as it is sequentially compact, what that implies every sequence in X has, therefore every sequence in X has convergent subsequence, which is Cauchy subsequence. Means every sequence in X has Cauchy subsequence, which implies XD is totally bounded. 1. Now we have to show that it is complete. Okay. Now to show XD is complete. XD is complete. For completeness, what we have to show? Every Cauchy sequence in XD is convergent. Okay. So for this, let Xn be Cauchy sequence in X. Now since X is sequentially compact, therefore Xn has convergent subsequence. Now Cauchy sequence in X is convergent if and only if it has convergent subsequence. We know. Xn is Cauchy sequence Xn is convergent if and only if it has convergent subsequence. Implies okay. So Xn has convergent subsequence. Xn is Cauchy sequence. So which implies Xn is convergent. Thus every Cauchy sequence in X is convergent, and therefore XD is complete. XD is complete metric space. So from 1 and 3, XD is complete and totally bounded. From 1, 3, XD is complete and totally bounded. Okay. Thus, every sequentially compact metric space compact metric space is complete and totally bounded. Conversely, we'll assume that XD is complete and totally bounded. XD is complete and totally bounded. Claim XD is sequentially compact. Claim XD is sequentially compact. Means what to show that any sequence has convergent subsequence. So for this, let Xn be sequence of points in X. Now since XD is complete, totally bounded, since X is totally bounded, implies Xn has Cauchy subsequence. Is it right? And since X is complete, which must be Xn has Cauchy subsequence, which must be convergent as X is complete. Implies Xn has convergent subsequence. Thus, every sequence in X has convergent subsequence. Every sequence in X has convergent subsequence. Therefore, XD is sequentially compact. Thus, complete and totally bounded metric space is sequentially compact. Thus, complete and totally bounded metric space is sequentially compact. So this is A, this is B. A and B proves the result. Okay, from A and B, the result is proved. A and B, the result is proved. So here we have seen necessary and sufficient condition, or sequentially compact metric space is equivalent to complete and totally bounded metric space. Okay. And then sequentially compact metric space is compact. Sequentially metric space is compact. That result also we have proved, means complete and totally bounded metric space is compact. Now we will take corollary. closed subset of complete metric space is sequentially compact if and only totally bounded. A closed subset of sequentially compact metric space is of complete metric space. Complete metric space is sequentially compact if and only it is totally bounded. It is totally bounded. Okay. So proof. Let A be closed subset of complete metric space XD. Then AD is complete. AD is complete. Additionally, if AD is totally bounded, if AD is totally bounded, then it is complete and totally bounded. It is complete and totally bounded, and therefore AD is sequentially compact. Conversely, suppose AD is sequentially compact. As it is sequentially compact implies AD is complete and totally bounded. Complete subspace is always closed. Since AD is complete, implies A is closed subset of X. Thus, result is proved. Okay. Next theorem, closed subset of compact metric space is complete. Corollary. Closed subset of compact metric space is complete. So let A be closed subset of compact metric space XD. A be closed subset of compact metric space XD. Now, since compact metric space is sequentially compact. Therefore, and closed subset of sequentially compact metric space is complete, and closed subset of closed subset of sequentially compact metric space is complete, implies A is complete. A is complete subspace. Next theorem, a totally bounded metric space is separable. A totally bounded metric space is separable. What is meant by separable metric space? If it has countable dense subset. So let XD be totally bounded metric space. XD be totally bounded metric space. Then for each n belongs to n, X has finite epsilon dense subset. Finite epsilon is equal to 1 by n dense subset. Say an for every n. Say n. Then A is equal to union of an's. N is equal to 1 to infinity. Is countable subset. Is countable subset of X. Claim A is dense in. Claim A is dense in X. Equivalent to A closure is equal to X. So let X belongs to A closure. And then B S R X intersection A is non-empty for every r greater than 0. Now for r greater than 0, choose n belongs to n such that 1 by n is less than r. Then 1 by n less than r. Now an is equal to say a1 a2 dot dot up to an is finite epsilon dense, is finite 1 by n dense subset of X implies, what this implies? Implies X is equal to union of S 1 by n A j. J is equal to 1 to n. And therefore, for X belongs to a closure, therefore, now X belongs to S 1 by n A j for some j belongs to 1 to up to n. Then d of x a j is less than 1 by n less than r, implies d of x a j is less than 1 by n less than r. What this implies? Implies AJ belongs to AJ belongs to SRX. That is to show, sorry. That is to show X belongs to a closure for every X belongs to X, which is equivalent to this, right? SRX intersection A is non-empty. Okay. This implies SRX intersection A is not equal to phi for every r greater than 0, and therefore X belongs to A closure for arbitrary X belongs to X, and therefore A closure is equal to X. Thus, X has countable dense subset. Therefore, X is separable. X is separable. So, with this discussion, we will stop our session here. Thanks for listening lecture carefully. Bye bye.